Welcome. I'm going to demonstrate using Rust to program a rack board, which basically encompasses this STM32WLE5 chip. So we're going to use this SoC and then let's get rid of that. And I'm just going to show you what I've got up here. So we have, I'm just going to just do a cargo build. Let me just clear this one time. Just show you. So ignore the warnings because this is, I'm not cleaning this up. I've disabled some configs that are important for later on because this config that I have here is something I just pulled out from an example and it's not working on this board. So I need to double check this in STM32WLE5. But with that out of the way, let's run my build debugger. So this is using the JLink Mini, and it's configured to use ProbeRS, and it's running it through VS Code. What I like about this workflow is that once it does work, let's try one more time. When it does work, it gives me a visual debugging flow through VS Code. And let's see. Right, so I noticed that it needs to be run twice sometimes. Let's just scroll up and focus on this part here. It shows the current config of the RCC. So I'm going to grab that here and actually just paste that into here as a comment. So when I come to troubleshoot this later on, it'll help me out figure out where things are going wrong. And I know this does work. Let me just read this through once again. So the sys clock, it's showing 4 kilohertz. Interesting. Yeah. But here we're configuring to 48 megahertz on Cisco. So I need to see what is happening here essentially. Yeah, this is like 4 megahertz from what I can see. I may be reading this wrong, but I can compare it to some other chips I worked on. But while that's going on, we can see some other information. If I scroll down, what I've done here is I've basically am accessing a peripheral. I'm not testing it just yet. We've got the PAO pin here, and we've taken the PAO port, which is on the rack chip. Let me find the data sheet for this thing, right? Here we go. So if we scroll into this, we can see PAO is kind of the LED one, and LED one is on pin 14. And that is basically the green LED on the board. And then we take it as an output. So if we go here, go to GPIO, we can see there's the output driver essentially. So this uses traits. It wraps a peripheral when you call new. You can specify the level and the speed. The level I've chosen to be low at start, right? And the speed I chosen medium. And then this lets you manipulate the driver as you like. And it takes the peripheral as owned, I believe, yeah. So once we do that, I'm just basically here, I'm just configuring the onboard RTC itself. And then we grab that. I'm setting the datetime now as this value. So I'm just, so this is wrong. This should be made today. And I just do a random time here. So I'm apply right now. And then we're just saying this one's there. Actually, we can remove this bit from here. We don't need to have a false delay up there. The I2C stuff is going to come in a bit as soon as I clean this up. I need to plug the RTC module. So the idea here is I'm going to have an external RTC as well, which is battery backed up. But I just want to show you how this very basic code is going to let me blink an LED. So it's just basically a Blinky, but at the same time, I'm also grabbing the RTC timestamp in through the debugger, rather than using UART and playing around with serial comms. And so this part is working fine. We've got a timestamp that is offset from the time since epoch. One interesting thing is this is a microcontroller. It doesn't have SD RAM connected to it, so I don't have alloc set up on it right now. So there's no global allocator. So that stuff I will sort of later on. Anyway, so we got that working. Let's just stop this for the moment. Let's go and just rebuild the changes, and we can now go back here and run the debug build again. This might need 2 tries, we'll see. I think it's working. Yeah. And it took the changes. It's only doing got RTC once. Oh, there's another one here. I guess, yeah, the reason this is here is because we're showing the original time. So I'll just say existing RTC time, UTC, and then we'll just say, yeah, so here we're updating it, right? And then it'll continue. So in reality, what will happen here is we would not do that. And here we would just fetch battery backed up time from RTC, from RV8803 RTC, and update MC, yeah, MC onboard RTC time. So the way this is going to work is we'll call that once it's all set up, and using this we can do that. So it'll be something like yeah, so this same function will be called later on. So let me grab that command from there and move that down here. So this will happen in here. Yeah. So this is just a quick intro to getting up and running and getting a simple Blinky going on STM32. There are some other small configs, like for example, we need to be mindful of our memory map, the address we flash it at, flash the device. Now, so for example, I'm flashing straight into address 00. Whatever RUI 3 firmware, yeah, bootloader, that's all white. There's no bootloader, right? This is bare metal, the direct output binary from Rust, which is this target release, no, sorry, thumb architecture. This file, rtc.d, this file is the one that we're going to, I think, open it. Okay, this is the binary. And this ELF binary is flashed directly into the flash, so into the EEPROM, and that's what's booting up, and we can see the actual output. Let me show you one more thing. I forgot, I couldn't show the breakpoint, so let's do that. Let's do something like, can I set a breakpoint there? That'll be good. Oh yeah, I need to show that to you as well. So let's try it again. It's nice because you can step through, and that's the whole point of this. So there we go. Oh, this is the beautiful part. Let me show this to you. So now We get to see the call stack. Remember, Embassy does have support for async, so we can do things like await. So that's great. We have peripherals. These are not because I have not uh, provided the file for that just yet. These won't do much on VS Code, but we can watch and we can see registers. The RCC config is showing up. Let's hang on, let me move this down. Oh, this is nice. Here we go. So now we can see straight away the RCC config, the PLLs, HSI is false. So the default config is visible, right? Oh, we get to see our peripheral, the LED2. This is the direct periph, and then I overwrote it with um, the output driver. And what's nice is we can see the pointer uh, where it points to essentially, and the other values. So we can do that. Now we can also try to step through. Let's do that. Let's just step over, and then it jumps straight over to where you can stop next. And then we can just do another jump, and it'll just we can basically keep looping through manually as needed. There are caveats. It does crash at times, so this is not always 100% reliable, but to a certain point, it lets you get to certain parts of your programming. It's far better to use tracing, this defmt, deferred formatting, output. So you can use debug, you can use different messages. So I can say, like, for example, let's just say something like debug, and then I can say something like LED to set low. Done. Right. And then let's do a couple of those. Let's just run this again. So this will you can have errors, you can have info, debug, trace as well. So you can say trace is grayed out here, and here we can see debug is in white. Trace is also and it's a lower level than debug. So this would ideally I would place as trace. But yeah. Okay. Well, catch you in the next one. I'm going to get the camera hooked up so you can see the LED blinking in the next one. Cheers. Bye.